Okay, so I'm going to talk about, it's hard to say this, quantum networking. A very specific aspect of quantum networking, which is creating entanglement. So I'm going to try to explain what is entanglement. I'm going to then explain what the purpose of this work is. This is actually an interesting work in that there was a hackathon for quantum networking, and this was at RIPE about, I think, last November. And I said, hackathon, so what are we going to do, write code for quantum computers? I had done a course in quantum computing, so I thought, maybe we'll write some code to do something. But it turns out we learned a lot about quantum networking, and we learned a lot about this phenomenon called entanglement. And one of the things that we learned is that entanglement is between two systems, but networking is multi-hop. So how do you get from entanglement between two systems and get to multi-hop thing? So I did what I do fairly consistently, which is, okay, let's write a draft. So there is actually a working group in the IRTF called the Quantum Internet Research Group in the IRTF. So this is the research task force. So we presented this there. So at the bottom, you can see the URL for this. The thing was to figure out what do you need to do to create quantum entanglement, and then from there, what do you need to make that entanglement multi-hop? So entanglement is this very, very quantum phenomenon where you have two particles and they share a state. So I'm just going to use spin, but you can do it with other things. You can have a particle that has either a spin up or a spin down. And you may not know what state it is in. This is the whole Schrodinger cat thing, where you don't know if it's up or down. You don't know if the cat is dead or alive. And then you make a measurement, and then you say, oh, it's up, great. But quantum entanglement is when you take two particles and you entangle them, and then they share the state. You don't know what the state is still, but they share the state. Then you can take them far apart, far away from each other. And then you measure one, and if that turns out to be up, then the other one will also turn out to be up. And Einstein didn't like this very much. He called it spooky action at a distance. The thing about this is it's really cool because you can use this to, it's probably the next slide, to do this thing called quantum key distribution. So you can't exchange information because the state is random, but you can exchange, it's almost like a one-time pad, where if you exchange enough of these bits and then you start measuring, Bob and Alice, of course, right? So Bob starts measuring and Alice says, hey, I see the same state. So they can actually exchange a random string, which can be the basis for for regular cryptography. So you're sharing a random secret, and you can use this as a private key for AES or whatever else you want to do. The other thing that's nice about quantum entanglement is you can't eavesdrop on this because that destroys the state, and then it can be detected by the parties at each end. So it's a nice way of sharing a secret and at the same time knowing that it's not been eavesdropped, that the man-in-the-middle attack can be detected. So it's important to note that QKD is not cryptography, it's just key exchange. So a little bit about the state of the art. When I went to RIPE, this was in Amsterdam, there's a company called QTech, which is about an hour away in a town called Delft. And QTech has been doing a lot of research on quantum networking. And so they have demonstrated a few things. One is entanglement, one-hop entanglement at a distance of 1.3 kilometers, which may sound underwhelming, but you got to get started, right? And then from there, they are trying to get this to work at 10 kilometers. The thing is that this entanglement is a very probabilistic process. So in order to actually create multi-hop entanglement, you have to know that you can create this entanglement relatively, on time. So the next, the third bullet here is deterministic entanglement, which is not that you're absolutely sure, but it comes up with high enough probability that you can try to have entanglement between A and B, and then between B and C, and then you can parlay that into an entanglement between A and C. And that's what's important for networking, assuming that you have a network of more than 2 nodes, which most people do. So here's basics. Here's your network. So you can call this a quantum network. And you have these quantum nodes, but associated with each of these quantum nodes, you have a classical control node, which could be just a server or could be a router. And the control node controls this quantum node. And so what you want to do is trigger that quantum node to create an entanglement or to do what is called entanglement swapping or various things. So the control node actually operates the quantum node. And so you have these classical links. And the goal here is to parlay one-hop entanglements. So you want to get this entanglement between these end nodes, but what you're going to get is an entanglement between adjacent nodes. So what we have today is the technology for creating an entanglement between 2 nodes. And like I said, we have this at 1.3 kilometers. We're trying to get it at greater distances. So how do you get from these sort of adjacent entanglements to something across the whole network? Well, you have to have a path. If you want to go from A to B, you have to know what are the hops you go through, and then create these entanglements across all these hops. And the choice of these hops is, what gives me the best entanglement, but not just the adjacent entanglements, but maybe the quality of the entanglement, the ability to swap the entanglement between, well, I should have put some names here, but between A and the next guy and the next guy and the next guy after that, I need to create an entanglement that now goes 2 hops, and then 3 hops, and then 4 hops. And so what's my ability to do that? So I have these path properties and node properties that I need to sort of have in the computation, so that I know that I can take these adjacent entanglements and create this end-to-end entanglement. So the question is, what is the topology of the network? What are the capabilities of each node? The number of communication qubits, the number of storage qubits, the operations you can do on these qubits. What are the capabilities of the links? So when I do create an entanglement, how long will it stay? What's the probability of creating that entanglement? How fast can I do the entanglements? And then there's this notion of distillation, where you take, maybe you create 2 entanglements between A and X, and then you create a better entanglement that might last longer or have higher fidelity. And then you take the entanglement between A and X and Y, and then create an entanglement from A to Y, and then A to Z, and then A to B, if you remember the diagram from before. So, so these are the questions, and this looks very much like a TE question. It looks very much like the extensions we made to link state protocols to tell you what are the properties of nodes and of links, and then you create a path with certain characteristics. In TE, you create a path that has enough bandwidth, TE, traffic engineering, or you create a path that has diversity from another path. Here, you create a path where the probability of creating a multi-hop entanglement is higher. So, yeah, that's me, right? You run a link state protocol for this. On the classical nodes, the classical node learns from the quantum node that it's associated with what are the properties of that node as well as of the links. And then you add these entanglement TLVs to the link state protocol, and then you are able to make the computation. So the end goal is, I'm just dying here, don't worry about me. It's not tuberculosis. So the goal is to create this multi-hop entanglement. And so you exchange these properties and then you compute these paths. So what you have is these things called fidelity. How good is my entanglement? But then I could have something that is high fidelity may not last very long or may take a long time to actually create. So what is the fidelity of an entanglement that I could create between two nodes? What's the number of qubits I have at a quantum computing node? The communication qubits are the ones that get entangled, but you can also put them in a storage qubit so that you hold on to that state for a while you do other operations. So you need to know how many communication qubits you have, how many storage qubits you have, and what operations you can do. It would be nice to know how many are available at a given point, but those things change a lot. And typically, we don't want to put things in a link state protocol that change quite often, because you'll melt the IGP by trying to get this information out there. What operations are possible on the qubits between the communication qubits and the storage qubits and among storage qubits? And what distillation processes you have to improve the fidelity of an entanglement. So you take two entanglements and create one entanglement from that, and hopefully it's a better entanglement. So the goal here was just to put this out there and have a discussion on what can we do here. So on the one hand, this hackathon that I talked about had this simulator that can simulate quantum networks and can try to really show what a network would look like if you had the right quantum properties. And the ability to do the quantum engineering to do all of this. So they're sort of looking ahead. The technology still has to catch up. The ability to create quantum entanglement at a distance, at lower temperatures, because typically all these things happen at 4 degrees Kelvin. Thank you so much. So the idea then is to say, okay, so you have this quantum simulator for a quantum network. This is cool, winter cool. If you now add, because you have at the same time the classical node and the quantum node, if you now add this property to the you start running a link state protocol first, and then you add this property to it, then you can say, how would this all work? And how would I actually create multi-hop entanglements? The other thing that, talking to the people at QTech, they focused on a particular realization of quantum entanglement. It's called nitrogen vacancy center in diamonds. So you basically, I'm getting way out of my depth, but you have a diamond crystal, and you replace 2 carbon atoms with a nitrogen and I think a proton. So you basically end up with a vacancy because you have a missing thing there. And then you use that to create qubits. And then you can do exchange of photons and have these qubits be entangled. But other people use different technologies. So there's ion trap, there's other realizations of quantum qubits, or communication qubits. So this was very much focused on how the QTech people do it, but the goal is to get other people to also say how they would do quantum entanglement, what kind of properties they would like to see, and how does this actually go. So we have this sort of overall architecture kind of draft that says kind of what's going on and what are the properties. We need drafts, sort of more details on how you capture this information. For example, if I talk about fidelity, what's the units and how do you actually express it in ISIS or in OSPF? and so on. So we need that draft, but we also need this feedback from other people to say how they would like to see this draft progress. If we get that far, then hopefully we write some prototype code and put that in this quantum simulator. And then we also take information from QTech's proposed 2-hop entanglement, which they're supposed to do this year. I'm not sure where they are exactly. And then from there, we actually see how this would go forward. So it was I think for me very interesting to learn the stuff. I had done a little bit of quantum networking, but to see these people, I got to spend a day in QTech seeing the researchers doing all this work. One caveat, this is not something that you'll see tomorrow, and the iPhone 12 is not going to have a little quantum processor in it. These things, I mean, the warm version of these run at 4 degrees Kelvin. The cold versions run at like point something Kelvin. So, and the technology is advancing. I think it'll advance non-linearly, but it's still quite a long way from being able to actually, exchange qubits or on the quantum computing side, you can break RSA, except we've got a literal handful of qubits, and you need lots and lots of qubits to break a decent-sized, to factor a decent-sized number. But I think this is interesting research, and I'm just happy to bring whatever I had to this. I did want to take longer so you couldn't ask me questions, but I'm here.